Hello, in this lecture we'll find out the length of line segment X using two different methods. In the drawing we have a semicircle that is inside a quarter circle. Here line segment AC is tangent to this circle at this point, and we also know that side AO equals to 6 units, and we want to find out the length of line segment AC that is actually equals to X. So we'll start with the first method. Here we will define the point of tangency of tangent AC with this semicircle as point D. And we will define the center of this semicircle as point P. Actually, because of the fact that we are talking here on a quarter circle, AOB is a quarter circle, this angle must be equal to 90 degrees, and point O is the center of the quarter circle. For that reason, AO is the radius of the quarter circle, because of the fact that line segment AO starts from the center of the quarter circle and ends at point A, that is a point on the quarter circle itself. And this is exactly the definition of a radius. So AO is the radius of the quarter circle. Likewise, for the same reason, OB, line segment OB, is also the radius of the quarter circle. That is to say, it is also equals to 6 units. So we know that the radius of the quarter circle equals to 6 units, but OB is not only the radius of the quarter circle, but it is also the diameter of the semicircle. So we know that the diameter of the semicircle equals to 6 units, and the radius of the semicircle is half of the diameter. And we know that the diameter of the semicircle equals to 6 units, therefore the radius will be equal to 6 over 2, that is 3 units. So OP is the radius of the semicircle that is equal to 3 units. PB is also the radius of the semicircle that is also equal to 3 units. And here we join points P and D together by a straight line. Here PD, line segment PD is also the radius of the semicircle, that is to say it is equal to 3 units, because of the fact that line segment PD starts from the center of the semicircle, that is to say from point P, and then at point D, that is a point on the semicircle itself. For that reason, PD, PB, and PO are the radii of the semicircle, because they start from those line segments starts from the center of the semicircle and ends at any point on the semicircle itself. And that is exactly the definition of the radius. That is to say, those three line segments are the radiuses, the radii of the semicircle. That is to say, they are equal to 3 units. Okay. In the next step, we'll join points A and P together by a straight line. And I will present to you a new rule that is actually rule number 1. According to rule number 1, a tangent to a circle, uh, the length the length the length of two tangents from a common external point to a circle are equal. So I'll read rule number 1 again. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So here we have this circle. If we have point P, this point is point P. Point P is an external point of this circle. Why point P is an external point of this circle? Because point P is not located inside this circle, nor on this circle, but it is located outside of this circle. Therefore, point P is defined as an external point in relation to this circle. So if from the external point P will draw two tangents to this circle, so if the first tangent so here is the first tangent. The point of tendency of the first tangent with this circle is at point A. And we'll also draw a second tangent to this circle. Here, this point, the point of tendency will be defined as point B. Point B is the point of tendency of the second tangent with this circle. And according to rule number 1, the length of two tangents, that is to say, the length of the first tangent is PA, and the length of the second tangent is PB. And according to rule number 1, the length of two tangents, that is to say PA and PB, from a common external point, that is to say from point P, because point P is defined as a common external point, to a circle, 2 points A and B are equal. That is to say, the length of PA equals to the length of PB, that is to say PA equals to PB. So according to rule number 1, whenever you draw from a common external point of a circle two tangents to that circle, then the length of those two tangents will be equal to each other. In this case, PA equals to PB. Okay, so we can implement rule number 1 in our drawing, because in our drawing we have the common external point, point A, and from the common external point, point A, we have two tangents to the semicircle. The first tangent is tangent AO. Tangent AO is tangent to this semicircle at point O. Point O is the point of tendency. And we have the second tangent, that is tangent AD. Tangent AD is tangent to this circle at point D. Point D is the point of tendency of this tangent with the semicircle. So we have, from a common external point, point A, we have two tangents to this semicircle, that is to say AO and AD, and according to rule number 1, the length of those two tangents will be equal to each other. That is to say AO equals to AD according to rule number 1. Okay, so here we write down that AO equals to AD according to rule number 1. But it is given us the question that AO equals to 6 units. So we can write here that AO equals to 6 units. And from this equation 6 equals to AO equals to AD, we will derive that AD is also equals to 6 units. AD equals to 6 units. So we can write here that AD equals to 6 units. In the next step, we will prove that those two right triangles congruent to each other. Actually, they congruent to each other according to side rule. So we will prove that the green right triangle, triangle AOP, congruent to the green right triangle, triangle APD. Actually, in triangle AOP, congruent, this is the sign of congruent, to triangle ADP, and they congruent to each other according to side rule. Okay. So I repeat on the reason that those two triangles can relate to each other. First of all, AO equals to AD equals to 6 units, according to rule number 1. In addition, AP is a common side, it belongs to both triangles, so AP equals to AP because it is a common side. AP equals to AP. It's a common side that belongs to both triangles. And finally, OP equals to PD equals to 3 units. Okay. OP equals to PD equals to 3 units. Actually, it is the radius of the semicircle, so we proved that all the sides of triangle AOP can relate to all the sides of triangle APD. Therefore, those two right triangles can relate to each other according to side rule. And from the fact that those two triangles can relate to each other, we conclude that those two angles are equal to each other, according to the rule that corresponding angles in congruent triangles are equal to each other. So here, angle OAP, this angle, equals to this angle, this is actually angle PAD, and those two angles that are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So those two triangles congruent to each other. Therefore, those two angles that are defined as corresponding angles that are located between, and they are they are inside the two congruent triangles AOP and APD, they will be equal to each other. Okay, so if we define angle OAP is theta, then from this equation theta equals to angle OAP equals to angle PAD, we derive that angle PAD is also equals to theta. Angle PAD is also equals to theta. So this angle PAD equals to theta. In the next step, we will connect points O and C together by a straight line. And in the green triangle AOP, the green right triangle AOP, we know that tangle theta equals to OP over OA. OP over OA. So here, triangle theta equals to OP, OP equals to 3 units, it is the radius of the semicircle, over OA, OA equals to 6 units according to what is given us in the question. So here, triangle theta equals to 3 over 6, we divide both the numerator and the denominator of this side of the equation by 3, and we get that triangle theta equals to 3 over 3 is 1, and 6 over 3 is 2. So in conclusion, we found out that triangle theta equals to 1/2. Okay? Triangle theta equals to 1/2. In the next step, I will present to you the law of cosines, and we will implement the law of cosines in triangle AOC. So, what is the law of cosines? The law of cosines is true in any triangle. So, if we have a triangle ABC, that could be any triangle. This is triangle ABC. And we know that side, 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 AB of triangle ABC equals to A units in its length. Side AC equals to B units in its length. And side BC equals to C units in its length. And the angle between side AB and side AC is theta. Then, according to the law of cosines, we will get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Okay, again, A squared plus B, C squared equals to A squared plus B squared minus 2 times AB times cosine theta. Okay. This is the law of cosines. That is for an right triangle. Now we will implement the law of cosines in triangle AOC. So I'll copy triangle AOC in this page, and we'll implement the law of cosines in triangle AOC. This is triangle AOC. AO equals to 6 units, AC equals to X according to what is given us the question. And what is the length of OC? O is the center of the quarter circle and C is the point of the quarter circle itself, and this is exactly the definition of a radius. That is to say, OC is the radius of the quarter circle that is equal to 6 units. So this is triangle AOC that I copied from the original drawing. Angle OAC equals to theta plus theta, that is 2 theta. Now we will implement the law of cosines in this triangle AOC. According to the law of cosines, this will be question number 1. We get that OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta so according to equation number 1, here CO equals to 6, so CO squared is 6 squared, that is 36, and it is equal to AO squared. AO equals to 6, so AO squared is 6 squared, that is also 36, plus AC squared. AC equals to X, so AC squared is X squared, minus 2 times AC 6 times AO is 6, here AO is 6, and AC is X times cosine 2 theta. Okay, so here we have 36 on both sides of equation number 1, so 36 will get cancelled. What is left of equation number 1 after we cancel 36? Here we have 0. On this side of the equation we have 0, that is equal to x squared. Minus 2 times 6 is minus 12. So this expression equals to, here also x, of course. So this expression equals to 12x times cosine 2 theta. Here we add to this expression 12x cosine 2 theta, and we get that according to this expression, x squared equals to 12x times cosine 2 theta. Cosine 2 theta. Okay. Here we divide this equation number 1 by x. It is allowable to divide the equation by x because x is the length of side AC. It can never be equal to 0, therefore it is allowable to divide this equation number 1 by x. So here x squared over x is x. Here x will get cancelled and we left only with 12 times cosine 2 theta. So in order to find out the value of x, the variable that we are looking for, the line segment that we are looking for, the only thing that we have to do is to find out the value of cosine 2 theta. Okay? Actually, we have trigonometric identity for cosine 2 theta. Cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. Okay, this is the trigonometric identity for cosine 2 theta. Cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. And we have already found out that tangent theta equals to 1 half. So we can substitute tangent theta in the trigonometric identity by 1 half. Here we already found out that tangent theta equals to 1 half. So we'll substitute tangent theta by 1 half in this trigonometric identity. And we'll get here that tangent cosine 2 theta equals to 1 1 minus tangens theta equals to 1 half, therefore tangens square theta will be equal to 1 half squared over 1 plus tangens theta squared, tangens square theta. Again, tangens square theta equals to 1 half squared. So here, this expression cosine 2 theta equals to 1 half square is 1/4, so I write it down. This 1 minus 1/4 over 1 plus 1/4. So here 1 minus 1/4 is 3/4, and 1 plus 1/4 is 4 quarters, 5/4. So here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled. In conclusion, we found out that cosine 2 theta equals to 3/5. Cosine 2 theta equals to 3/5. Now we can substitute cosine 2 theta in equation number 1 by 3/5. Okay, because cosine 2 theta equals to 3/5. According to equation number 1, x equals to 12 times cosine 2 theta, and cosine 2 theta equals to 3/5. So x equals to 12 times 3 is 36 over 5. X equals to 36 over 5. That is to say, x equals to 7.2 units. Okay. X equals to 7.2 units. So here AC that is equal to x, it is equal to 7.2 units. 7.2 units. So we finished with the first method. In the next step I will present to you how to find out the value of side AC that is equal to x according to the second method. In the second method, we'll use all the fields that we have already found out in the first method. Okay. The center of the semicircle is at point P. The point of tangency of tangent AC with this semicircle is at point D. We already found out that OP equals to 3 units, P equals to 3 units, and also PD is the radius of the semicircle, that is to say it is equal to 3 units also. We join points A and P together by a straight line, as we did in the first method. We already found out that angle AOB, this angle equals to 90 degrees. And we already found out that triangle AOP can relate to triangle APD according to side rule. Triangle AOP, congruent, this is the sign of congruence, to triangle APD, according to side rule, and from the fact that those two triangles congruent to each other, we conclude that those two angles, they are both equal to each other, and if one angle equals to theta, then the other angle must be also equal to theta, because those two angles are equal to each other. And here, from here, we'll do a construction. So until this step, all the things that we did until now have already been done in the first step. In the next step, we will do something that we didn't did in the first step. We will extend line segment AC, and we will also extend line segment OB by a straight line until they intersect with each other. Okay? Repeat again, we extended line segment AC and line segment OB by a straight line until they intersect with each other. At this point, we define the intersection point of the two extended line segments as point E. So we actually created here a right triangle that is right triangle AOP. In the right triangle AOP, line segment AP is angle bisector. Line segment AP is angle bisector. So we can implement the angle bisector theorem in the triangle AOE. But first of all, I will present to you what is angle bisector theorem, and then we will implement the angle bisector theorem on the right triangle, triangle AOE. Okay? So, here, what is angle bisector theorem? Angle bisector theorem. So what is angle bisector theorem? If we have triangle ABC, that could be any triangle. This is triangle ABC. We also have line segment AD is angle bisector of angle BAC. Because of the fact that it bisects angle BAC into two halves, it defines as angle bisector. So AD is angle bisector. Okay? I'll write it down. AD is angle bisector So according to angle bisector theorem, the angle bisector in a triangle divides the side that it hits here. Angle bisector AD hits side BC. So can I tell that in this case I'm relating to side BC. So actually the angle bisector BC and the angle bisector AD divide side BC into two parts. The first part is BD, and the second part is DC. Okay, so the angle bisector in a triangle divides the side that it hits in a ratio that is equal to the ratio between the two legs of the angle that is bisected into two halves. In this case, it is angle BAC, and therefore we relate to side AB and side AC of the two legs of angle BAC. Side AB and side AC are the two legs of the angle BAC that is been bisected into two halves. So, and the ratio between the legs of the angle that has been bisected into two halves is AB over AC. And that ratio, according to angle bisector theorem, is equal to the ratio that angle bisector AD divides side BC, and the ratio that angle bisector AD divides side BC is equal to BD over DC. In conclusion, we found out that BD over DC equals to AB over AC. Okay? We can write down also that AB over AC equals to BD over DC. That is to say, the ratio between the legs of the angle that has been bisected, that is to say AB over AC, equals to the ratio that angle bisector AD divides side BC. And that ratio equals to BD over DC. In conclusion, AB over AC equals to BD over DC. Okay? I repeat again. The ratio between the angle's legs, the angle that has been bisected into two halves, the ratio between its two legs is AB over AC. And that ratio equals to the ratio that angle bisector AD divides side BC. And that ratio equals to BD over DC. In conclusion, we found out that according to angle bisector theorem, in the right triangle ABC, AB over AC equals to BD over DC. Okay, so we can implement rule number 1 in triangle AOE. So I'll copy the right triangle AOE in a new page and we'll implement the angle bisector theorem in the right triangle AOE. So actually, this is the right triangle AOE that I copied from the original drawing. In the right triangle AOE, we have angle bisector AP. AP is angle bisector. AP is angle bisector. We write it down that AP is angle bisector. Why it is angle bisector? Because of the fact that it bisects angle OAE into two halves. Each half equals to theta. And according to angle bisector theorem, the ratio between the legs of the angle that has been bisected into two halves is AO over AE. Or we can also say that the angle that has been bisected into two halves is OAE, and the legs of angle OAE is OA and AE, and the ratio between the two legs is OA or AO over AE, and that ratio equals to the ratio that angle bisector AP divides side OE. And the ratio that angle bisector AP divides side OE is OP over PE. Okay? So this will be question number 1. Again, the ratio between the angle, the legs of the angle that has been bisected into two halves we are talking on angle OAE, and its legs are AO and AE, and the ratio between its legs is AO over AE. And this ratio equals to the ratio that angle bisector AP divides side OE. And the ratio that angle bisector AP divides side OE, angle bisector AP divides side OE into two parts, OP and PE. And the ratio between those two parts is OP over PE. And that ratio equals to the ratio between the angle's legs. And the ratio between the angle's legs is AO over AE. So in conclusion, AO over AE equals to OP over PE. Here AO equals to 6 units according to what is given us in the question. AE is AE, and it is equal to OP. OP is the radius of the semicircle, that is to say it is equal to 3 units. PE is PE. Okay? So in conclusion, we found out that 6, according to equation number 1, 6 over AE equals to 3 over PE. Here we will divide equation number 1 by 3, and we will also multiply it by PE. We'll multiply it by AE. So we get that 6 over 3 equals to AE over PE. 6 over 3 is 2. So here 2 equals to AE over PE. Here we will multiply this equation number 1 by PE, and we get that according to equation number 1, two times PE equals to AE. We define PE as A. Again, PE equals to A according to our definition. So you can write down that PE equals to A. And here also PE equals to A. So according to equation number 1, AE equals to 2 times PE, and PE is A, so PE equals to 2A. According to equation number 1, AE equals to 2A. Here AE equals to 2A. Okay? In the next step, we will continue to focus on the right triangle AOE, and we will implement the Pythagoras theorem on the right triangle AOE. Okay, so copy again the right triangle AOE in a new page, and we will implement the Pythagoras theorem on the right triangle AOE. Okay. We have already found out that AE equals to 2A. So we can write here that A equals to 2A. And here TE, side OE of the triangle AOE equals to 3 plus A. Okay, OE equals to 3 plus A. So I can write down here that side OE of the right triangle AOE equals to 3 plus A. This is the right triangle AOE. We will implement the Pythagoras theorem on the right triangle AOE. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This will be question number 2. The square of the hypotenuse is AE squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AO squared plus OE squared. Okay? So AE equals to 2A. Therefore, AE squared, I'll repeat again, according to the Pythagoras theorem, AE squared equals to AO squared plus OE squared. A equals to 2A, so A squared is 2A squared. And it is equal to AO squared. AO equals to 6, so AO squared is 6 squared, that is 36, plus OE squared. OE equals to 3 plus A, so OE squared will be equal to 3 plus A squared. So according to equation number 2, we found out that 2A squared equals to 36 plus 3 plus A squared. We'll open the brackets on both sides of equation number 2, and we get that according to equation number 2, 2A squared is 4A squared, and it is equal to 36 plus 3 plus A squared. 3 plus A squared equals to 3 squared, that is 9, plus A squared plus 6A. So 4A squared equals to 36 plus 9 is 45, plus A squared plus 6A. Here we'll subtract A squared from this equation, equation number 2, and we get that according to equation number 2, four A squared minus A squared is 3A squared. Equals to 6A plus 45. Here we'll divide this equation number 2 by 3, and we'll get that according to equation number 2, A squared over 3 is A squared, and it is equal to 6A over 3 is 2A, plus 45 over 3 is 15. We subtract 2A and 15 from this equation number 2, and we get that according to equation number 2, A squared minus 2A minus 15 equals to 0. So we have here a quadratic equation. The coefficient A in this quadratic equation is 1, the coefficient B is minus 2, and the coefficient C is minus 15. And the general solution for a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Now a specific quadratic equation, the variable that we are looking for is a, so x equals to a. So we'll put the data inside the formula for x and we'll find out the value of the values of a because x equals to a. So a equals to minus b, b equals to minus 2. So minus b is minus 2, that is plus 2, plus minus square root of b squared, b equals to minus 2, so b squared equals to minus 2 squared, that is 4, minus 4 times a is 1, times c, that is minus 15, over 2a, 2 is 1, a is 1, so 2a is 2 times 1, that is 2. So we found out that a equals to 2 plus minus 4 times minus 15 is plus 60, and 60 plus 4 is 64. So inside the root we left only with 64 over 2. So here a equals to 2 plus minus the square root of 64 is 8 over 2. We have two solutions that are possible for a. The first solution for a is a1 equals to 2 minus 8 over 2. 2 minus 8 is minus 6, and minus 6 over 2 is minus 3. So we found out that a1 equals to minus 3, but because of the fact that a is the length of line segment PE, so a as a length must be a positive number. A of a1 is a length, it must be a positive number. Therefore, it can never be equal to minus 3, that is a negative number, so we cancel this solution and we left only with the second solution, that a equals to, or a2 equals to 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So we found out that a equals to 5. A equals to 5. We can write here that a equals to 5. If a equals to 5, 2a is 2 times 5, that is 10. That is to say, AE equals to 10 units. So what is the length of line segment BE? The length of line segment BE, from the drawing it is very easy to see that BE equals to PE minus PB. PE minus PB. I'll repeat again. From the drawing it is very easy to see that B equals to PE minus PB. So BE equals to PE is A, that is equal to 5, minus PB. PB is 3, that is the radius of the semicircle. So in conclusion, we found out that B equals to 3 minus to 5 minus 3, that is 2. So BE equals to 2 units. Here, BE, found out that BE equals to 2 units. So we can write here that BE equals to 2 units. Likewise, we find out the value of line segment CE. What is the value of line segment CE? From the drawing, it is very easy to see that CE equals to AE minus AC. AE minus AC. So CE equals to AE, that is 10 units, minus AC, that is equal to X, according to what is given as the question. So in conclusion, we found out that CE equals to 10 minus X. C equals to 10 minus X. We can write here that CE equals to 10 minus X. So in the next step, we will complete the quarter circle to a circle. So we completed the quarter circle to a circle. In the next step, we will extend line segment BO by straight line until it touches the circle. And we will define the touching point of the extended line segment BO and the circle as point M. What is the length of MO? O is the center of the circle and also the center of the quarter circle, and M is a point on the circle itself. And this is exactly the definition of a radius. That is to say, MO is the radius of the quarter circle, that is also the radius of the circle, that is equal to 6 units. So MO equals to 6 units. Okay? So in the next step, I will present to you a new rule. That is actually rule number 3. Going to rule number 3. If two chords intersect with each other outside the circle, at point P. So point P is the intersection point of the two chords outside the circle. Then the following equation is true. So we have your two chords that intersect with each other at point P. So this is the external point P outside the circle. And we have chord AB, this is chord AB, that intersects with chord CD, this is chord CD. So chord AB intersects with chord CD outside the circle is point P. Point P is the intersection point. So here, according to rule number 3, we will get that PA times PB equals to PC times PD. Okay, I'll repeat again. PA times PB equals to PC times PD. Okay? So in our drawing, we can implement rule number 3 in our drawing. This is actually rule number 3. This is rule number 3. We can implement rule number 3 in our drawing because in our drawing we have chord AC that intersects with chord MB. Again, chord AC intersects with chord MB at point E. Point E is the intersection point of chord AC with chord MB. So, and point E is outside the circle. The intersection point is outside the circle, therefore we can implement rule number 3 in our drawing. So I write it down. I repeat again that chord AC intersects with chord MB at point E. Point E is the intersection point of chord AE with chord MB. Therefore, according to rule number 3, we will get that, I repeat again, chord AC number drawing, chord AC intersects with chord MB at point E. Therefore, according to rule number 3, we get that EC times EA equals to EB times EM. EB times EM. I'll repeat again. According to rule number 3, in our drawing, EC times EA equals to EB times EM. Again, EC times EA equals to EB times EM. And here, EC equals to 10 minus X, EA equals to 10 units, and it is equal to EB, that is 2 units, times EM, that is 6 plus 3 plus 3, that is 12, 12 plus 2 is 14, so EM, in conclusion, equals to 14. So according to rule number 3, we found out that 10 minus X times 10 equals to 2 times 14, 2 times 14 is 28, so write it down. So 10 times 10 minus X equals to 28. Here we divide this equation by 10 and we get that 10 minus X equals to 28 over 10 is 2.8. We will add to this equation X and we'll subtract 2.8 and we get that X equals to 10 minus 2.8, that is 7.2. So found out that X equals to 7.2 units, exactly as we found out in the first method. We finished with the second method. In the next step, I will present to you, I will summarize the lecture. We'll start with the first method. So I repeat on the question. We have here a semicircle inside the quarter circle. AO equals to 6 units. Side AC is tangent to the semicircle at this point. And we want to find out the length of side AC, that is equal to X. Okay, so first of all, we defined the center of the semicircle as point B, and we defined the point of tendency of tangent AC with this semicircle as point P. because of the fact that this is a quarter circle, this angle must be equal to 90 degrees. That is to say, angle A or B equals to 90 degrees. And AO is the radius of the quarter circle because of the fact that point O is the center of the quarter circle and point A is the point of the quarter circle itself. And this is exactly the definition of a radius. For the same reason, OB is also the radius of the quarter circle. That is to say, OB also equals to 6 units. But OB, it is not only the radius of the quarter circle, but it is also the diameter of the semicircle. So we know that the diameter OB of the semicircle equals to 6 units, and the radius of any circle or semicircle is half of the diameter. That is to say, the radius of this semicircle will be equal to 6 over 2, that is 3 units. So here OP equals to PB, and then we join points P and D together by a straight line, and PD is also equals to the radius of the semicircle. All those line segments OP, PB and PD exit from the center of the semicircle and touches the circle itself, either at point B, at point O, or at point B. And this is exactly the definition of a radius. That is to say, those are the radii of the semicircle that is equal to 3 units. And we also join points A and P together by a straight line. And then I presented to you rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So here we have this circle and we have the point P, that is the external point of this circle. Here from point P we draw two tangents to this circle. The first tangent is tangent PA and the second tangent is tangent PB, and then the lengths of those two tangents will be equal to each other. That is to say, PA equals to PB. So we can implement rule number 1 in our drawing, because in our drawing we have the common external point A is an external point in relation to the semicircle. From the common external point A we have tangent AO and tangent AC. Two tangents, and according to rule number 1, they must be equal in their lengths. That is to say, AO equals to AD according to rule number 1. But it is given as the question that AO equals to 6 units. Here AO equals to 6 units, and from this equation 6 equals to AO equals to AD, we will derive that AD is also equals to 6 units. Here AD is also equals to 6 units. Then we actually proved that those two right triangles can congruent to each other according to side rule. Why they can congruent to each other according to side rule? First of all, side AO equals to AD equals to 6 units. AO equals to AD equals to 6 units. AP is a common side, it belongs to both triangles, so AP equals to itself as a common side that belongs to both triangles. AP equals to AP. And here also OP equals to PD equals to 3 units. This is the radius of the semicircle. Okay, OP equals to AD equals to 3 units. So all the sides of triangle APD can go to all the sides of triangle AOP. Therefore, those two triangles can go to each other according to side rule. Okay, triangle AOP can go to triangle ADP according to side rule. And from the fact that those two right triangles can go to each other, we will conclude that those two angles are equal to each other according to the rule that the corresponding angles in congruent triangles are equal to each other. Those two right triangles can go to each other, therefore the two corresponding angles must be equal also to each other. So angle OAP equals to angle PAD, And if we define one angle is theta, then the other angle must be also equal to theta because we find that they are equal to each other. Then we focus on the right triangle AOP. This right triangle AOP, tangent theta equals to OP over AO. In the right triangle AOP, tangent theta equals to OP over AO. Here OP equals to 3 units. AO equals to 6 units. So in conclusion, tangent theta equals to 3 over 6. We divided both the numerator and the denominator of this side of the equation by 3. And we got that 3 over 3 is 1, 6 over 3 is 2. So in conclusion, we found out that tangent theta equals to 1 half. Okay, tangent theta equals to 1 half. Then we joined points O and C together by a straight line. And I presented to you the law of cosines, and we implemented the law of cosines in this triangle AOC. So what is the law of cosines? The law of cosines is true in any triangle. So if we have this triangle ABC, that could be any triangle. Side AB equals to A units in its length, side AC equals to B units in its length, and side BC equals to C units in its length. And the angle between side AB and side AC is theta. Then according to the law of cosines, C squared equals to A squared plus B squared minus 2 times AB times cosine theta. So actually we can implement the law of cosines in triangle AOC, and copy triangle AOC in this page. Here OC, what is the length of OC? O is the center of the quarter circle. C is the point of the quarter circle itself, and this is exactly the definition of a radius. That is to say, OC equals to the radius of the quarter circle, that is actually 6 units. So OC equals to 6 units, AC equals to X, and AO equals to 6. And the angle between side AO and side AC, or angle OAC equals to 2 theta. Yeah. Here OAC equals to OAC equals to 2 theta. So according to the law of cosines, we get that OC square equals to AO square plus AC square minus 2 times AO times AC times cosine 2 theta. Okay, so OC equals to 6, so OC squared is 6 squared, that is 36, and it is equal to AO squared. AO equals to 6, so AO squared is 6 squared, that is 36 also, plus AO squared. AO equals to X, so AO squared is X squared, minus 2 times AO, that is 6, times AC, that is X, times cosine 2 theta. Here we have 36 on both sides of equation number 1, so 36 will get cancelled. And what is left for equation number 1 after we cancel 36? What is left is that in this side we have 0, on the other side we have x squared minus 2 times 6 is minus 12. So this expression equals to, in conclusion, to minus 12x cosine 2 theta. We added 12x cosine 2 theta to this equation number 1, and found out that x squared equals to 12x times cosine 2 theta. Then we divided this equation number 1 by x, and we found out that x equals to 12 times cosine 2 theta. So the only thing that is left to do is to find out the value of cosine 2 theta, and in this way we will find out the value of x, that is the 9th segment that we are looking for. Okay, and in order to find out the value of cosine 2 theta, actually we have trigonometric identity for cosine 2 theta. Cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. We already found out that tangent theta equals to 1 half. That is to say, we can substitute tangent theta in the trigonometric identity by 1 half. We did it, and we got here that cosine 2 theta equals to 1 minus tangent square theta. We know that tangent theta equals to 1 half, so tangent square theta will be equal to 1 half squared. Okay, so here in the numerator we have cosine 2 theta that is equal to 1 minus 1 half squared over 1 plus times theta squared. And times theta squared equals to 1 half squared. So it is actually here 1 plus 1 half squared. That is times theta squared. So here cosine 2 theta equals to 1 half squared is 1 quarter. So in the numerator we have cosine 2 theta equals to 1 minus 1 quarter over 1 plus 1 quarter. Here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled. And we're left only with cosine 2 theta that is equal to 3 over 5. So now that we know that cosine 2 theta equals to 3 over 5, we can substitute cosine 2 theta in equation number 1 by 3 over 5. So according to equation number 1, x equals to 12 times cosine 2 theta. And we substitute cosine 2 theta by 3 over 5. And found out that x equals to 12 times 3 is 56 over 5. So x equals to 36 over 5, this is 7.2 units. Okay, we finished with the first method. In the next step, I will present to you how we found out the value of line segment x according to the second method. In the second method, we used all the things that we already found out in the first method. Here we have the center of the semicircle is at point P, the point of tendency of tangent AC if this semicircle is point D, OP equals to PB equals to PD equals to 3 units. This is the radius of the semicircle, and this angle equals to 90 degrees. Point O is the center of the quarter circle, and those two triangles can point to each other according to the first method, and therefore those two angles are both equal to theta. In the second method we did another construction. We extended line segment AC and we extended line segment OB until by a straight line until they intersect with each other at point E. Point E is the intersection point of the extended line segment OB and the extended line segment AC. So in this way we created the right triangle, triangle AOE. In the right triangle AOE we have AP is angle bisector, that is to say it divides angle OAE into two halves. Each half equals to theta. Notice the reason that AP, line segment AP, is defined as angle bisector because it divides angle OAE into two halves. Okay, what is angle bisector theorem? Angle bisector theorem is if we have triangle ABC, that could be any triangle, and we know that angle AD is angle bisector. Why angle AD is angle bisector? Because of the fact that it divides angle BAC into two halves. Each half equals to theta. And we have the angle bisector theorem that states that the angle bisector in a triangle divides the angle that it eats in a ratio that is equal to the ratio between the two legs. Okay? Again, according to angle bisector theorem, we get angle bisector theorem states that the angle bisector in a triangle divides the side that it is, that is to say BC, in a ratio that is equal to the ratio between the two legs of the angle of the angle that has been bisected into two halves. In this case, it is angle BAC. So, according to angle bisector theorem, the angle bisector AD divides the side that it is into two parts. Angle bisector AD is side BC, and it divides this into two parts. The first part is BD, the second part is DC. And the ratio between those two parts is BD over DC. But that ratio is equal to the ratio between the angle's legs, between the angle that has been bisected into two halves, between the legs of the angle that has been bisected into two halves. The angle that is bisected into two halves is angle BAC, and the legs of angle BAC is BA and AC, and the ratio between those two legs is AB over AC. Okay, the ratio between the legs of the angle that is bisected into two halves is AB over AC, and that ratio equals to the ratio that angle bisector AD divides side BC, that is actually equals to BD over DC. In conclusion, AB over AC equals to BD over DC. Okay, so we can implement the angle bisector theorem in our triangle AOE. So I'll copy triangle AOE in a new page, this page. This is the right triangle. The angle bisector AP divides angle OAE into two halves, each half equals to theta. And according to angle bisector theorem, we get that the ratio that the angle bisector AP divides side OE, that is actually OP over PE, equals to the ratio between the angle's legs. The angle that has been bisected into two halves, and the legs of angle OAE that has been bisected into two halves by angle bisector PA is OA and AE. Again, the legs of the angle that is bisected into two halves is OA and AE, and the ratio between those two legs is OA over AE, and that ratio equals to the ratio that angle bisector AP divides side OE, and the ratio that angle bisector AD divides side OE is OP over PE. In conclusion, we found out that OA over AE equals to OP over PE, according to angle bisector theorem. OA equals to 6 units, AE is AE, OP equals to 3 units, this is the radius of the semicircle, over PE. PE is PE. We divided this equation by 3, equation number 2, and we multiplied by AE. So we found out that according to equation number 1, actually, 6 over 3 equals to AE over PE. 6 over 3 is 2. So we multiplied this equation by PE and found out that 2 times PE equals to AE. So AE is twice as long as PE. So we defined PE as A, here PE equals to A, and here also PE equals to A, according to our definition. Now in equation number 1 we have 2 times PE equals to AE, but PE equals to A according to our definition. That is to say A equals to 2 times PE, that is 8, A equals to 2A. A equals to 2A, A equals to 2A. and P equals to A according to our definition. Okay? In the next step, we implemented the Pythagoras theorem on the right triangle, the same right triangle, triangle AOE. Okay? This is the right triangle AOE. We already found out that A equals to 2A, A equals to 2A, OP equals to 3 plus PE. 3 plus PE is 3 plus A, because PE equals to A. So here OE equals to 3 plus A. You can see it from here also, that OE equals to 3 plus A. Okay, OE equals to 3 plus A, AO equals to 6, and the hypotenuse A equals to 2A. So according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AE square equals to AO square plus OE square. A equals to 2A, so AE square is 2A square, plus OA square. OA equals to 6, OA square is 6 square, that is 36. Plus OE square. OE equals to 3 plus A, so OE square is 3 plus A square. We open the brackets on both sides of equation number 2, we found out that 2A squared is 4A squared plus 36 equals to 36. And we open the brackets here, 3 plus A squared equals to 3 squared, that is 9, plus A squared plus 6A. 36 plus 9 is 45. So in conclusion, we found out that 4A squared equals to 45 plus A squared plus 6A. We subtracted A squared from this equation, equation number 2, and found out that 4A squared minus A squared is 3A squared. 3A squared equals to 6A plus 45. Here we divided equation number 2 by 3, and we found out that 3A squared over 3 is A squared. 6A over 3 is 2A, and 45 over 3 is 15. So here we subtracted 2A and also 15 from this equation, equation number 2, and found out that A squared minus 2A minus 15 equals to 0. So we have here a quadratic equation. The coefficient A equals to 1, the coefficient B equals to minus 2, and the coefficient C equals to minus 15. And the general formula to solve a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the missing variable, that we are looking for is a, so x equals to a, and we have the coefficient abc. So we put the data in the formula in order to find out the value of a, because x equals to a. So here a equals to minus b, b equals to minus 2, so minus b is minus 2, that is plus 2, plus minus square root of b squared. B squared equals to minus 2 squared, that is 4, minus 4 times ac, a is 1 and c is minus 15. Over 2a, a is 1, so 2 times 1 is 2. So here we have a equals to 2 plus minus. Inside the root we have minus 4 times minus 15 is plus 60, and 60 plus 4 is 64. So inside the root, what is left is only 64. Okay? So here we have a equals to 2 plus minus square root of 64 over 2. Okay? And the square root of 64 is 8, so here we have a equals to 2 plus minus 8 over 2. So here we have two solutions that are possible for a. The first solution for a is a1 equals to 2 minus 8 over 2. 2 minus 8 is minus 6. And minus 6 over 2 is minus 3. So we found out that a1 equals to minus 3. But because of the fact that a is the length of sine PE, it must be a positive number. A can never be equal to minus 3, that is a negative number, so we cancel this solution and we left only with the second solution. A2, that is equal to 2 plus 8 over 2. 2 plus 8 is 10 and 10 over 2 is 5. So we found out that A equals to 5 units, PE that is equal to A equals to 5 units. And if A equals to 5 units, 2A is 2 times 5, it is 10 units. So A equals to 10 units, PE that is equal to A equals to 5 units. And then we found out the length of line segment BE. From the drawing you can see that BE equals to PE minus PB. Okay, BE equals to PE minus PB. PE equals to 5 units, it is A. And PB equals to 3 units, it is the radius of the semicircle. Okay, here PB here PB equals to 3 units and P equals to 5 units, so B equals to PE minus PB. PE is 5, PB is 3, so B equals to 5 minus 3, that is 2. So we found out that BE equals to 2 units. Likewise, we found out the value of line segment CE. For the drawing, it is very easy to see that CE equals to AE minus AC. AE minus AC equals to CE. CE equals to AE minus AC. AE equals to 10 units and AC equals to X. This is the variable that we are looking for, the line segment that we are looking for. So in conclusion, we found out that CE equals to 10 minus X. Okay? In the next step, we completed the quarter circle to a circle, and then we extended line segment BO by a straight line until it intersects with the circle at point M. Point M is the touching point of the extended line segment BO and the circle. So what is MO? O is the center of the circle and the center of the quarter circle. M is the point on the circle itself. And this is exactly the definition of a radius. That is to say, MO equals to the radius of the circle, that is also the radius of the quarter circle, that is equal to 6 units. Then I presented to you rule number 3, and we implemented rule number 3 in our drawing. So what is rule number 3? According to rule number 3, if two chords intersect with each other outside the circle, in our example is at point P, they intersect with each other outside the circle at point P, then the following equation is true. So we have this circle, and in this circle we have chord AB and chord CD. Those two chords intersect with each other outside the circle at point P. Point P is the intersection point of the two chords. Therefore, according to rule number 3, the following equation is true, that PA times PB equals to PC times PD. Again, PA times PB equals to PC times PD. Okay, so we can implement rule number 3 in our drawing, because in our drawing we have chord AC, chord AC intersects with chord MB at point E. Okay, chord AC intersects with chord MB at point E. Point E is the intersection point between those two chords that is outside the circle. Therefore, according to rule number 3, we get that EC times EA equals to EB times EM. Okay? EC times EA equals to EB times EM. EC equals to 10 minus X, EA equals to 10, EB equals to 2, and EM equals to 6 plus 3 that is 12, 12 plus 2 is 14. So in conclusion, EM equals to 14. EM equals to 14. 2 times 14 is 28. So here we have 10 times 10 minus X equals to 28. We divided this equation by 10 and we found out that 10 minus X equals to 2.8. Here we added X to this equation and we subtracted 2.8 and found out that X equals to 10 minus 2.8. 10 minus 2.8 is 7.2 units. So we found out that X equals to 7.2 units. So in both methods, we found out that the length of line segment AC that is equal to X is equal to 7.2 units. Okay, thank you very much.